There. Okay, we are in recording mode now. There's several different things I want to talk about the quiz. And I've mentioned that there's a 60% rewrite opportunity. That's any question you got less than 60% on that you can rewrite to get up to 60%. But also, there were several of you that I could tell you know this stuff. And you know how to take derivatives now, and you got the answer quickly. But I said show your work, okay? And if you lost any points, if you got it correct and didn't show your work, and I took something off for that, you show your work and turn that back into me, and I'll give you full credit. The idea was show your work was part of this is a 1,000 level class. I've got to make sure you have the understanding and you're not just floating through, that you do have the basics down, okay? So I do want to say, if I ever said work or with the question mark and I took something off for it, you've got an opportunity to finish that problem, show the work that you did to get the answer, and I'll give you credit for that, okay? Even if it's above 60%, all right? But in general, the rule of thumb is if you got the thing totally wrong or you didn't do it, feel free to show your work, do it clearly, and get up to 60% on any question that you didn't get. That'll be great review for the test tomorrow, okay? Yeah, any questions on that?
I have a question.
Yeah.
If we do the rewrite, where do we submit that?
If you can, since it's not going to be an online thing, that will be an opportunity, probably send it as an attachment to an email. If you could just take a picture of your work, make sure you send both. Make sure you let me see the original. And if you either write on it with the new, write in a different color, pencil or pen or something, and let me see the difference, or else put the original and then make a second page of a couple people have done that. The second page is really clearly done on a separate piece of paper. But several of you it fit really nicely on the original, but did it in a different color, or box it in so it's obvious the work that you're doing there, and just take a picture and send it as an attachment. That'll be great.
Okay, thank you.
All right, thanks for asking. And yeah, I know you were one that I know you know, and you did it right. But gee, I just want you to show your work on that, okay, Diamond? I appreciate that. Does anybody else have any other quick questions about that? Okay, in a little bit, I'm going to go through an in-class problem that I'm going to include on the test tomorrow, a first derivative test question, all right? And I didn't include that on the quiz. I did do a second derivative test, and some of you need to look at that a little bit better. But I want to talk first about the basics of the quiz. So what I think I might do, I'm going to go to, I think I'll talk through it first, and when we come to a point of wanting to say something, I'll tell you what, I'm going to go over to my iPad now, okay? I'm going to go to my iPad, and there's some things I want to say from the beginning about question 1. Okay, that's something we're going to be doing soon. That's for the in-class problem. There's a problem that we're going to be doing. Let me see here. So I got to go to a new share. All right, so what I want to do is, all right, I got to get out of here in order to do that. Okay, so I'm going to stop share, and I'll be right back, okay? I need to go to clear my screen on the iPad. I was trying to do it. Lord have mercy. Okay, so here we go. I'm going to go to the iPad now. Okay, so one of the things I want to say about the intervals, when I ask you guys to put intervals for your answers, one of the things, the situations is, you've got to stop and think. The original problem that we had on the quiz was shaped like that. We had that, let me get the original problem down there. It was x to the third, a positive x to the third. And then there were some other goodies. And that is indicating that it's got the curves going on, all right? But I want to talk about the intervals. Some of you started and ended some of your intervals in inappropriate locations, okay? So if we're talking about increasing or decreasing intervals, stop and think about it. Where do those intervals end? When we've got a function like this and there's nothing that's undefined, so it's a polynomial and it's defined in the whole situation, it's all going to be, where's the slope equal to 0? The critical numbers. So when you've got a critical number, it's where the slope is going to be equal to 0. And notice that's where increasing and decreasing changes. So it's going to be, the critical number is going to be that point of change. So it's going to go, like this one's going to go from negative infinity to this critical number. This is increasing. And this is starting from this critical number to positive infinity. Okay? And then, you okay with that? Okay? And the decreasing segment is going to go between the two critical numbers. On that problem that we did, what was it? -3 and -1? -3 and -1. So -3 to negative infinity to -3, and then from -1 to positive infinity are both the increasings, and the decreasing has those again for the endpoints. The critical numbers are the endpoints, is what I'm saying, and infinity. Okay, when you've got this. So a few of you did something slightly different than that, and that's not ideal. Another situation. Any questions about that? Okay, another situation that's come up is with when you're looking at concavity. Some of you picked just different arrangements for your endpoints. So stop and think about this, concavity. Remember what a point of inflection is. Point of inflection is where, a point of inflection is where it changes from concave down to concave up, or concave up to concave down.
Yeah, I did see some droplets on the seat, but.
Okay, well listen, you might want to mute your mic. A few of you, I'm hearing some conversation, it's background. I guess I can mute you too, but if you can mute your mic, that'd be cool. Okay, so remember, this is where the point of inflection is where the concavity changes. So that's going to be the endpoint, okay? In this case, again, it turned out to be exactly halfway between -3 and -1, so it was -2. But the concavity, that's where it changes. Concave down stops at x equals -2, and concave up starts at -2. So concave up and concave down start and stop at the point of inflection. And there may be more than one in a problem. And I've been typically choosing problems that aren't super complex for sake of taking derivatives and that kind of stuff, keeping it basic. But when you get to other calculus like Calc 2 and stuff, you're gonna have multiple points of inflection, and those are the starting and end points of concavity changing, concave up and concave down. Okay? Any questions about that at all? Okay, so let's see. Yeah, so increasing and decreasing, it's got to do with where it is the critical points, the ending, starting and ending on that situation. Any other questions about number 1 that anybody would like to ask? Or number 2, because number 2 is related to the same graph. Don't feel funny if you've got a question, okay?
So what would the concavity intervals be? Concave up and concave down? Would it be negative infinity to -2 and then -2 to infinity?
Exactly, exactly. And all of these, you guys, that is exactly correct. And so all of you also, all of these, because the starting and ending, there weren't any undefined moments. This part here, concave down, is right there, and concave up is right here. That's exactly correct. And for both of these questions, notice in every case, I used open parentheses. At the endpoints, it's not increasing or decreasing. The slope is 0. So it's not appropriate to end with a closed bracket, okay? When you're talking increasing and decreasing and you've got a slope equals 0, that's neither increasing or decreasing. That's an endpoint, okay? It's an endpoint, but you don't include it. So it's open intervals, always. When I'm asking for those intervals of increasing or decreasing, it's possible sometimes you could have circumstances where the endpoint will be a closed bracket, but not for the increasing, decreasing thing when the endpoint is a slope of 0, is a critical point. And the same thing with concavity. Concavity is changing. Second derivative equals 0 there at a point of inflection. So where it's 0, it's not positive or negative. Therefore, it ends at the point of inflection, and that's got an open bracket. Always, these are all open parentheses. Okay?
I got a question for you.
Go ahead, say it again.
So if you have an inflection point or a critical point that the the numbers getting closer to as the limit gets to that specific point of x,
Yes.
what kind of notation do you use if that point doesn't exist, but it exists all around it?
Right. And that, if you, everything except that one pixel, right? Like, yeah, well, the idea is that you just use an open bracket. That covers every, open parenthesis type thing. So that means you're getting closer and closer and closer, but you never get there.
Okay, so you'd use a bracket on that side, and then on the other side, it would be a parenthesis.
Bracket if there is a closed situation, if the endpoint is counted on one end. That's the only time you use it. And on these situations we're talking about, the endpoint would not be counted. There could be circumstances where the endpoint would be counted, like if you've got a different kind of interval that isn't a continuous curve, it's a interval that's got a bracket or something like that, it could be that you include that endpoint. But on all of these, none of them would be included as an endpoint. So they would all be open parentheses.
All right, sweet, thank you.
Okay, good. Anything else at all? Okay, great. One other thing about the second derivative test in number 2, you guys, though, if you look on the bottom of the quiz, at the very bottom of the formula sheet, I put the first derivative test rule, the wording, and the second derivative test wording. So notice on the second derivative test, what you do, remember this now, is you take the derivative, you got to have the critical points, you take the critical points, that's important. So for like in this problem, -3 and -1 are the critical points. So then when you take the second derivative test, when you use the second derivative test, what you plug into the second derivative are the critical points. So you take the second derivative and plug in -3 and -1. That's in there, that's not at the point of inflection, so it's going to be part of the curve. And the situation, so in our case, let's look at this real quickly. I'll do this quickly. I know you've got it in front of you, but the derivative is 3x squared plus 12x plus 9. And the second derivative then of x is 6x plus 12. Okay? So the second derivative test is you plug in -3 into second derivative. This right here. So you've got f double prime of -3, and you've got f double prime of -1. This is doing the second derivative test, plugging the critical points into the second derivative. All right? You'll see that in the definition. It says c, f double prime of c, and that is a critical point that you determined in the first derivative, set equal to 0. Okay? So in this case, you would end up with what? -18 plus 12, which is -6. And the positive plug in -1, and you get -6 plus 12, which equals plus 12, which gives you +6. Now, there were a few of you that put this -6 and this 6 as the y coordinate to some answer, okay? These are not. If you're trying to find the value of something, you got to go back, you got to plug it back into the original function. You got to go back, that's f of -3. If you want to find what the value is at the critical point, several of you you took the second derivative and you set it equal to 0, and you got -2, for instance, and then you plugged in -2 and got 0. You plugged it into the second derivative and got 0. So several of you got -2, 0 for your answer for the point of inflection, okay? And that's not it. You got to plug -2 back into the original function, okay? So if you plug it into the second derivative function, then you're going to get 0, okay, every time. But you plug it, if you want to find the coordinate, then you plug it into f, the original function. So you got to go back up to f of -2 and get -2 to the third plus 6 -2 squared plus 9 -2 plus 2. Pardon me for going off to the edge there. But that's equal to what? -8. That's 4 times, positive 4 times 6. And then we've got -18 plus 2. And that ends up giving us, what do we have? -26. What did I plug it into? Why am I getting 0? -2 is the point of inflection. Oh, because is the answer 0? It is. Oh, it is 0. And in this case, it turns out to be 0. So that is correct. So you do get 0. Everybody okay with that? So yes, the point of inflection turned out to be -2, 0. Is that right? Let's see here. Okay. So any other questions about that now? Any questions at all?
Yeah, so we can use the second derivative test to find the -2, but we can't, right?
You can use the second derivative test to tell, remember the goal. The goal typically in the section that was working in was the second derivative test was to determine whether you've got a max or a min. You've got the
I don't mean the test. I mean like just we can use the second derivative and set it equal to 0 to get the x coordinate, right?
Yes, but it doesn't guarantee it. Second derivative equal to 0 it's a possible inflection point, okay? They talk about that a little bit in the text. So you can't assume because the second derivative is equal to 0 there, that it gives you the desirable end of that's an inflection point. So for instance, tell you what, let's do one that's x to the 4th. If we use f of x, this is off the cuff, so I'm trusting that this is going to work fine, all right? So let's look at the second derivative of this, okay? And part of the situation is there's things that happen. Okay, so yeah, so you can see, what is the general shape of this? It's going to be a U. It goes up to the left and it goes up to the right. There's no point of inflection in this, okay? But when you take the second derivative and set it equal to 0, you get 0. So the first derivative equals 4x to the third, and the second derivative equals 12x squared. And notice if you set that equal to 0, the answer is 0. But that's not a point of inflection, okay? So setting the second derivative equal to 0 and solving for it, it worked on the other polynomials we've got, but it doesn't guarantee it. So if you pick a number to the right and to the left of 0 for this situation I just drew there, it would both be positive, and that means it's concave up on both sides, so that's not a point of inflection, okay? That's the test they're saying you got to do. That if you have a situation and you set it equal to 0, you get a value that doesn't guarantee that it's a point of inflection. Because that would happen right here. If we've got 12x squared equals 0, well, x equals 0. Got it. X squared equals 0, so x equals 0. But that's not a point of inflection because it doesn't change from being concave up to concave down there. It's concave up on the left and it's concave up on the right. So if you plug in -1 or +1, you get a positive value both times. So it's concave up on both sides. Okay?
Yeah,
Questions
so
on that?
what method do we use to find the inflection point? If we do that.
So the idea is if you take the second derivative, set it equal to 0, you've got a possible point. Then you got to plug it in. Pick a number to the right and to the left. Like, let's do this one right here. So I've got this, the function is x to the 4th. So I take the second derivative, set it equal to 0, I get x equals 0. I pick x equals 1, and I pick x equals -1. And plug it into the second derivative. And I get 12, 1 squared, which is 12, which is positive. If I plug in -1, I get 12, -1 squared, that's equal to 12. Positive. They're both positive. Therefore, it's not a point of inflection. If you take the second, you plug them into a second derivative, one should be positive and one should be negative if it's a point of inflection. Okay? And in our situation, that doesn't. Okay?
Yeah, thank you.
Okay, good. And when you get into Calc 2 type stuff, you're going to have a variety of different types of functions that aren't as obvious as the ones we have here, the nice smooth curves. And they're going to be, and you got to have in mind that I got to take the second derivative and pick a number to the left and to the right and verify, the situation. So that's part of this. It's almost too basic right now, and it's almost too easy, and it's distracting to you. But at the same time, that's what you're going to have to do with thicker stuff downstream. Okay. Okay, let's keep going. Something else I wanted to say is on number 3, question number 3. What was that? Yeah. On question number 3, we were talking about, oh yeah. Okay, so you have a function, and I just picked a parabola, okay? You're gonna have a lot more complex functions than that when you have situations. But you take the function, you take the derivative, find any critical points between the endpoints of the interval of your concern, you need to check. Critical points and the endpoints. There were a handful of you that went in and plugged in every number between -3 and +2. You did -3, -2, -1, 0, 1, and that defeats the idea of what we're talking about, okay? The idea is you pick, the only thing that's going to be totally correct on that is if you pick the critical numbers where the slope is 0 and the endpoints. And in this case, there was only one. You took the derivative, set it equal to 0, you got x equals -1. So all you had to do was check -3, -1, and 2 back in the original function because you're trying to find the absolute max and min value of the function, right? So you don't plug that back into the derivative. There were a few of you that plugged it into the derivative and that threw things off a bit. So you got to plug, you're trying to find the max and min value that's of the function. So you got to go back to f itself, okay? Any questions on that?
Might not be a question about that, but more along the lines of the optimization problems with the area that you can take up with a set amount of fence.
Okay. So what do you think?
Well, I'm struggling with just the different ways to do it. So I understand that the one on the quiz, I believe, had a wall on one side, and you had to figure out the square footage of the area that could be covered.
Yes.
I was curious if you might be able to run through one of those, for example.
That's number 4, right? We're talking about number 4s. So if somebody else has something for number 3, we can come back to it, but let's go on to number 4. Go ahead and finish what you're asking. That's right. You got 3 sides, and the third side is taken up with something else. That's right.
Yeah, so like I remember on the homework there was one where it was kind of like this, and then there was another one in the middle, and
right.
I really kind of had no idea how to go about doing that one.
Right. And the whole thing there was I picked one where one of the sides you only had one of them. Okay? You have one y and there's 2 x's. Okay? Well, the one they ask you to do in the book is there's 2 y's on that rectangle because there's no river on that third side. All 4 sides are counted. So you got 2y plus 3x equals the footage. Let me call up, I'm going to go back to my iPod for a second and show you this. And because this is real life situations are going to be more like this than the sweet, yes, I've got y by itself and I can do this myself type situation. But the diagram they had was this was the situation that you had. And the way they worded it, it wasn't clear that the y's were completely one side. You know, it looked like you might have to figure out the lengths of those sides too. But if these two are the same to be y, and all of these three now were going to be x's, okay? And let's pick a number. I think the problem they did in the book was it 1800 or something like that? I think it was 1800. Well, that's what we used. So the situation would be that you've got 3x plus 2y equals 1800. Okay? So in order to get to y by itself, now we still got to do, and they want the area. They want to maximize the area. So you've got the fencing equation. This is the amount of fencing. Okay? So that might have started with the original function being f fencing equals 3x plus 2y. And then they tell you got 1800 meters, I think. They use meters of fencing. So now that's our equation. Well, the other equation is we still got area, and that's equal to x times y. And you're trying to maximize the area. So that means you're maximizing this one. So that means you got to take the derivative of that. Find the one thing you're trying to maximize or minimize is what you got to take the derivative of. So the other equation, because they gave you a value, you can get the y by itself and put it in terms of x. And therefore, let's plug it in. So this one's a little more complicated because the y isn't by itself. But let's look what happens when we do this. So if I get the 2y equals 1800 minus 3x, all right? Now to get to y by itself, I've got to divide by 2. And there's a couple different ways you could do this. You could divide 2 by both sides completely. But if I also divide this by 2, notice this is an even number. And it could end up being that y equals 900 minus 3/2 x, or 3x over 2, or whatever. And now you substitute this in here, multiply that out, and notice you get an x squared term. So you get an inverted, and it's going to be negative. So you get an inverted parabola. It's going to have a maximum function at the peak. So plug that in, multiply it out, take the derivative, and you got a little bit of a fraction you got to contend with. Sometimes we have tendencies, if you had 2y equals 1800 minus 3x, to divide this side by 2 and divide this whole side by 2. So you've got this mess over here, okay? If you do that, it can be a little bulkier and clumsy, but notice if I just divide each term by 2, this turned into something that could be quite manageable. And you end up with area equals x times 900 minus 3/2 x. And now I multiply it out, and I got a term with the x squared. So I'll just finish this, and then we'll go on to the other questions, okay? X squared, so the area, so there's our area function in terms of, we finally got it to be just in terms of x. Now take the derivative, set it equal to 0, answer the questions. And do what you did with the easier problem, all right? So that is that situation. And again, real life, Calc 2, they're going to be more challenging than the fencing problem, okay? But I'm probably going to stay with something very basic on the test to make sure you got the foundations down. And this isn't an algebra trying to make sure you got the algebra down. I'm trying to make sure you get the concept of taking the derivative, maximizing the area, and that's the calculus portion of it. So any other questions about that?
Dr. Renta?
Yes.
The next problem you do, can you do the second L'Hopital's rule?
Yeah. I tell you what, before
Okay.
we do that, let me just talk about number 5 real quickly, okay?
Thank you. Yeah. No
That
problem.
specifically. Okay, I'll tell you what, let's go to the second one. You requested it, let's do that. I'll do the second one. All right, so I'm gonna go to number 6, you guys, 6B. Or is it 6? Yeah, it was, I think. Okay, so let's do that. All right, the first one, notice the first one was that the limit is x. I'm going to do the second one. The limit as x goes to infinity of x squared over e to the x. Okay, so the first one, you guys, one of the biggest things about the L'Hopital's rule question, you got to make sure it qualifies for L'Hopital's rule. If it doesn't qualify, sometimes if you start taking the derivative of this thing top and bottom, it's going to take you a different direction than what it really does. It doesn't work because it doesn't go to 0 over 0, or it doesn't go to infinity over infinity. There were several of you that didn't check. So I took off a good chunk of that. That is foundational to L'Hopital's rule working, okay? So you need to make sure the first thing you do, that first problem, plug in 0 where x is. And you get 0 over 0. Show that, check it, and show that you did that, and now you take the derivative of the top and the derivative of the bottom, okay? So that's a crucial part of that problem. There were several, more than a few of you did that. You did the problem derivatives correctly.
You
But
get 0
you
over
don't check
1.
it. Go ahead, Thomas.
Wouldn't you get 0 over 1?
No. Because
Anything to the power of 0 equals 1, right?
oh, you're talking about the first question was the limit as x goes to 0. This second one is the limit as x goes to infinity.
Oh, I thought you were talking about this one. I was like, I'm getting real confused. I'm sorry about that.
My bad. The first question, the final answer was -1, okay? And you plug in zeros and you get 0 over 0. Okay, well in this one, if you take x squared to infinity, that's going to infinity, all right? So if you plug it in just like it is, thanks for speaking up, Thomas. That might have been confusing for someone else too. But as x goes to infinity, x squared goes to infinity. And as x goes to infinity, e to the x goes to infinity. That's primary. That is crucial for determining, now I can use L'Hopital's rule, okay? Again, that's where several of you didn't do that. That's an important part of it. So now, this function equals, so this function is equal to, that's why I kind of like to do it off to the side so the string of equalities would work. I would go up here and show this is infinity over infinity. And therefore now, and I wouldn't have written it over here like this. So I can now just write an equal sign that's saying this is equal to, and several of you are still not writing equal signs. I'm going to start knocking off you guys. If you do not include equal signs and you're finishing your problem, it's going to be less than a perfect paper, okay? It might be A work, but that's not A work if you're not putting equal signs. Mathematical equivalence is crucial, and that sign is going to be a mainstay for you on your way through the process, okay? So the equal sign is, now this is equal to the limit as x goes to infinity of the derivative of x squared is 2x, and the derivative of e to the x is e to the x. And now, if I take the 2x to infinity, I get infinity. If I take e to the x to infinity, I get infinity. So again, it qualifies for another L'Hopital's moment, okay? And so now, this string of equalities is important because this second one, where I'm going to take the derivative on the top and the bottom, the limit is exactly the same answer as the top one. The limit for the first, the second, and the third are all the same. So this, when you get the answer to this one, it still applies to the original problem that you started with. The equal signs belong. Take the derivative of 2x, I get 2, e to the x. Now I don't get infinity on top, okay? Now I get 2 over, and this isn't, plugging in and saying, I plug in infinity and I get that. Well, infinity is not a number. But this thing is going to infinity. E to the x is going to infinity. So, and as that goes to infinity, you know the top is a constant, therefore this is going to 0. So the limit as x goes to infinity of that is now 0, and the final answer is 0. Okay, any other questions about that? All right, good. Anybody want to see part A? Just a thumbs up or say yes, and I'll do it. Okay, the biggest thing is that people got wrong was not checking to see if you get 0 over 0. You do, but if you don't check it, then L'Hopital's rule, you don't know for sure, okay? And you're using it, could be inappropriate. Okay, let's go look at number 5 real quickly. Number 5 had to do with the gravity problem, and it's got to do with we're up 64 feet off the bottom, and something's being projected across the top. And one of the things is the function was given to be negative 16t squared plus 48t plus 64. And you guys, on the formula sheet, you'll see I'll give that. I'll also tell you that this is s of 0 and this is v sub 0, you know. So the initial velocity, yes, that goes there. And we'll work with that next section, this last section of the text, developing this formula, taking antiderivatives and coming up with the formula to start with. But that this is the velocity, 48 feet per second, and this is the starting point of 64. But several of you, the biggest mistake on this one, it happened with more than a few times, was taking the derivative of that first term. Several of you did not get negative 32t. I know you know that. Some of you got 24, and some of you got negative 48. You gotta slow down. You gotta slow down and do the math. Take the derivative of each term. Make sure you get negative 32t plus 48, okay? Set that equal to 0. Several of you also are not plugging in 0 anywhere into all your functions, okay? You somewhere set this equal to 0 and solve for t. Part of the math of it is you're setting it equal to 0. It isn't equal to 0 just because it's there. You factor this, yes, that doesn't make it equal to 0. You have to, the mathematics of it is you set it equal to 0. The math of it is you need to make that step, okay? So that's an important part of the deal also. Let's see, other things that happen. You know what? There were a handful of you, more than a couple, okay? When I say a handful, probably 4 or 5, that did get, when you got 1.5 for this answer, you got this, you even wrote this. And then you didn't get the correct answer here. Somehow you've got to make sure you're using the calculator right. Several of you did not get, what is it, 100, I think? Part B is the max height. That turns out to be 100. So watch this now. Whatever you're doing on your calculator, I think you're whirring through it, and you maybe did negative 16 times 1.5 and then squared that. I don't know. I'm not sure what you did. But this is negative 16 times 2.25 plus 1.5 times 48, that's 24, that's 72, plus 64. And you end up with here, that's negative 32, and negative 4 makes negative 36, plus 136 equals 100, okay? And use the increments 100 feet. So there were several of you that I know you did this right, so I'm trying to give you credit for it, but you gotta be able to use your calculator, you guys. That you came up with, a couple of you came up with 0, a couple of you came up with 100, I saw 144. There were different numbers that came up, and you just gotta be careful with this, okay? That part of it, you gotta make sure you get solid. Any other questions on that? Okay, and then one of the things we hadn't done a lot of, let me just finish with this, because when the last question said, when does it hit the ground? And that's when S of t equals 0, okay? And that's equal to negative 16t squared plus 48t plus 64. So if you have this set equal to 0, you factor out, you could right now use the quadratic formula and get the answer. When you got the formula of negative b, it's on the formula sheet, negative b plus or minus square root of b squared minus 4ac all over 2a. Well, a equal to negative 16, b equal to 64, and 48, and c equal to 64 gives you the answers. It gives you, what are they, 4 and negative 1? You get that, all right? But factoring it down, knocking off the negative 16 makes it simpler. You can still use the quadratic if you do this. Negative 16 goes into there once. 16 times 3 gives me 48. Got to change the sign. Times 4 gives me 64. Got to change the sign. That's crucial. And now, if you wanted to, you could use the quadratic formula, where a equals 1, b equals negative 3, and c equals negative 4. And you would end up with 4 and negative 1. Or you can factor this, which is t minus. And so t minus, and it's got to be 4 and 1, and the negative's got to be, so it ends up being, whoops, so it's got to be plus 1, right? Negative, yeah, so we end up with t minus 4 equals 0, t plus 1 equals 0, t equals 4, t equals minus 1. Minus 1 is a negative time, makes no sense. In our diagram, it does make sense because it's back here at negative 1, but 1 put us up here, 1.5 put us at the top, 2 put us even with this one, 3, 1.5 plus 1.5 gave us 3 seconds here. This is 2, that's 1.5. Here's 1, 1.5, and this is 4 down here. Okay, and negative 1 back here. This is 0 here. Okay, so it works out. You can factor it, you can use the quadratic formula, etc. Any other questions about that? Any part of it you'd like to clarify? A couple of you, I'm sorry about that, but you left off SEC, you know. One of you put S for, and be careful, M is what? Meters? Is that meters? Is it miles? What are we talking about? So, you know, putting the word down would be a most complete answer to make sure you are clear about what your answer is. Seconds, you know, say it. That'll be a good habit to get into. Any other questions about this quiz? You can do the rewrites on it. You can do the rewrite, keep it if you want to review it, look at it for the test, reviewing for this. This will be a good prep for the test, etc. Go from there. But any other questions about that at all? Okay, what I want to do now is I want to move over to doing the in-class problem, okay? And I've got that set up here. I'm going to go back to, the situation of putting it on my desk, and let's go from there. So what we're going to do is we're going to put on my desk. Okay, let me open it up. Let me open up the file. And that is right. That's not it. Okay, you guys, I'm sorry about this. I noticed a couple different times that I had killer wasting of your time, and I apologize for that. But part of what I wanted to do is I want to call up the, I'm going to go back to our main screen of the class and go to, so what I want to do now is go back to our class, and I will select the ICP. I'm going to open ICP 5 back on the site, okay? So it is now going to be open. Okay, in-class problem set 5 is open. I'm going to call it up here to look at it. Okay, so here is what I ask you to do. And this is the first derivative test. I want to go through this process of doing a first derivative. You can look on the second page. I've included it on the second page here also. I've included it on the second page here. But if you notice, the first derivative test down here is saying, it gives the rules, what you got to do. You know, it gives the statement about it. The second derivative is there also, but this is the first derivative. Take a look at it. So the idea is you take the derivative and you've got to look to the left of the critical number and to the right of the critical point. When you find the critical points, you got to look to the left and to the right, okay? So do this with me right now. Let's find the critical points of this problem, of this function. We got to take the derivative, set it equal to 0. All right, so let's go over here to my iPad. All right, have you gotten the critical numbers, the critical points, values? I hope so.
Negative 1 and 6.
What are they again? Say it again.
Negative 1 and 6.
Negative 1 and 6. Okay, now notice, you guys, I intentionally picked one that starts with the negative sign in front of the cubic. Okay? So when I ask you for a sketch, it's not like our typical ones. All right? It's not like our typical ones because it's been all positive x cubed. This is negative. What does that look like? It's going to look like this time. So the min is going to happen here, and the max is going to happen here in order. Before, the max happened first as you move left to right, and then the min happened. But this one is shaped like this. So I intentionally did that. So what do we get? So we got negative 6x squared plus 30x minus 36. Factor out a negative 6. And I get x, oh yeah, I get negative, right? Yeah. So I get x squared minus 5x plus minus, that's a minus 36, so that makes it a plus 6. Yes? Okay, and now we've got a minus in the middle, a plus on the end. So that turns out being, did I factor that right, you guys? I took the negative out, so that makes it a positive here, makes this
that's
a
right.
negative, and makes the last one a positive, right? That's correct. Everybody agree?
Yeah.
Okay, negative 6. So now I'm going to factor this. I get x, x. I get positive, so the signs have to be the same. Negative in the middle, so it's got to be, they both got to be negative. I got to get a multiple is 6, and the sum is 5, 2, and 3. Is that right? So the 1 and the 6, we look at that again. What might have happened is you might have moved a little bit too quickly on the factoring, okay? And you got to be careful about the fact that I know where that 1 and 6 came from. Looking at this, you got 5 here. Yeah, I could multiply 6, and the difference of the two would give me 5. But notice they both have to be the same sign. So you don't want a difference. So it's got to be a sum. So it turns out to be, it turns out to be factoring to be negative 2 and negative 3 are the factorization. Everybody okay with that? Okay, so now let's set this equal to 0. My concern is where this equals 0 and this equals 0. Okay, that means x equals 3 and x equals 2. So look what's happening here now. So go back to my sketch. 2 and 3 are the two critical numbers, right? This is the shape. Where's the slope equal to 0? At 2 and at 3. I don't know where it is on the graph, but it's in this kind of relationship. 2 is here, 3 is here. X equals 3, okay? That means right now, if I stopped, okay, so all I'm doing, all this is talking about we're finding we're doing the first derivative test, right? So look at the sketch, see that, the first derivative test, all we're trying to do is determine, is this a max or is it a min? You can see at 2, we got a min. At 3, we got a max. But I want you to do the first derivative test means you need to include the next step. You need to take a number to the left of 2, x value, a number between 2 and 3, and a number bigger than 3. We're going to the right of 3, stay as small an integer as you can. I'm going to go to 4. In between, we got to use a decimal. Sorry about that, or a fraction. That means we got to do 2.5. 2.5 is a value. And to the left of 2, since we know they're both there, we could use 1 or 0. Let's just use 1. I'll pick 1. 1's an easy one to work with also. So there's our 3 values. Your first derivative test, you want, what is the slope at these 3 numbers? So you need the slope. These 3 need to be plugged into f prime. So you need f prime of 1, you need f prime of 2.5, and you need f prime of 4. All right? So this, you need those 3 values and determine if the slope is positive or negative. That's all you need to know. Calculating will be good practice, but you get some complex situations and you can find out right now if it's positive or negative, but if it's 1,287 positive or negative, it can turn into a mess. But if you can tell it's positive right now, that's fine. Okay, let's look at 1. So I'm going to go to, notice there's the derivative here. We got a couple different things to look at. One of them is, this is the first derivative right here, a factored form. And we can also plug it back into the original form, okay? Now, plugging in 1, you could plug it into either one, it's pretty straightforward, but when you plug in 1, that's pretty easy to plug in the original function, you know? Because you plug in 1 for the x's and the signs are already there and everything. So for the first one, I'm gonna plug 1 into the first function, all right? And that gives me -6 times 1 plus 30 times 1 minus 36, which is minus 42. What do we have there? So we got -6. What are we expecting it to be? The sign is going to be positive or negative?
You're missing a squared on the -6,
Right.
1.
Yeah, I'm sorry. I kind of, you're right. That's good. I thought that, but I got the squared and it was +1. So I put that. So good call. You're right. That's squared. That's right. But notice that that's 1. So we end up with -6 plus 30 minus 36, which is minus 42. So you get -12. The answer is negative. Does that match our diagram, our sketch? Yes. If it doesn't, flag something. That's a flag view. You did something wrong. Either the sketch is wrong or your calculation is wrong. So this is negative over here when you plug in 1. Now, what is it? You okay? Okay, now look in between. Now in between, plugging in 2.5 into the original function is a mess. But look at the second function. Look what I've got right here. This one. 2.5 is real close to 3. It's real close to 2. That could be a real easy thing to do. So this is equal to -6. That -6 is crucial though for keeping the right sign, okay? And then I've got x, 2.5 minus 3 times 2.5 minus 2. That equals -6 times -0.5. And this is +0.5. I don't need that plus sign, but I'm just reinforcing. We got negative times a negative. That makes it 3. That makes it 1.5. So, but the big thing is that it's positive 3/2 or 1.5. And it is positive. Okay? So, you okay? And that makes it positive in between. Notice that matches our sketch. I think the sketch can be a big plus to know if you understand it correctly and get it squared away. And then again, this is the first derivative test. I'm taking the long drawn out approach. When you get moving and you just move through it, include this stuff, you can get done fairly quickly. Okay? So look at this. You can plug it into either function. I think the plugging 4 into the breakdown like this again is going to be easier. 4 minus 3 times 4 minus 2, -6 times 1 times 2, -12 again, that's negative. I got a negative value at 4. That's negative there. So to answer the question, what does the first derivative test tell you? Well, I've got a negative slope here that goes down to 2, to x equals 2. And then from 2 to the right, it goes up. Therefore, this is a min. So a local min is at x equals 2. We'll plug it in a second and figure out the y value. What is the min? A complete answer, you can say it's at x equals 2, but what is the min? That is part of a correct answer, okay? And then the local, notice the other one, if you've got a positive, it's positive between 2 and 3, and it's negative, right? It's positive between 2 and 3, and it's negative to the right of 3. What now? Between 2 and 3, it's positive. Yeah. So at x equals 3, what was the function we were looking at? That was 2. 2.5 was halfway, and my drawing got a little strange there. So what we got is this. No, it's not that. It is this. We did this one. We checked here and got that that's a min. And now we're looking for the max. So in between, we got positive slope. To the right, it's negative slope. It goes down. Therefore, in between, it had to be a peak. All right? So at x equals 3, we had to have a peak there. That was the peak, the situation. So it's a local max at x equals 3. All right? Now notice that's not the max. The max is the value of the function. So for both of these numbers, I need f of 2 to find out what the min is. And that is going to be equals, let's see, -2, 2 cubed plus 15, 2 squared. I'm going to move it down, pardon, minus 36, 2 plus 7. That's equal to 8. That's minus 16. That's 4 times 15 is 60. Minus 6 plus 7. That gives me 1 here. This 1 here at 61 minus this, so that's equal to 45. Do you all get 45 also? Positive 45, is that it? Yeah. Okay, so that ends up being, so that is 245. And let's look at the local max. Plug in x equals 3. And I'm going to plug that in up here. I got a little more room. So I get -2, excuse me, 3 cubed plus 15, 3 squared minus 36, 3 plus 7. And I end up with, that's 27 times -2 is -54. 15 times 9, what do we have there? Is that 135? And then minus 108 plus 7. So I end up with, this gives me minus 108 plus 7 is minus 101. That makes this a plus 34. So I've got -54 plus, let me do that again. Anybody have the answer yet? That's
Yeah,
positive.
I had gotten that the
What'd you get?
f of 2 is -21 and the f of 3 is -20. I'm looking at your f of 2 and it looks like you made the -36x just -3.
Okay, I hear you. Everybody see that? -2, yeah, that's correct. I thought the answers were negative both. And you know what, you guys? Another thing to check it. Look with me on this. Graph it. Look at this. I put it on Desmos. Okay? And can you see this now? Do you see this on Desmos on your screen?
Yes.
Okay, look at this. This is where the graph is. Look where the answers are. Yes, I'm going to zoom in. Okay? Zoom in a little bit more. Look what's happening. Where my low is at 2. Where my high is at 3. Look where I'm at. -21. -20. So yeah, you're right. That's exactly right. When I did this problem last night, I was thinking, why did this turn out positive? What happened on my math? Do you remember? Do you see what I did? -2.
Yeah, you had changed the -36 in your f of 2 to just a -3.
Oh, f of 2 is -2 times 2 cubed and plus 15, 2 squared is positive 60. Am I right? Am I missing what you said?
Yeah, it's the next term, the -36 times 2. You have that as -3 times 2.
Oh. Regular. I see it. Now I see it. Okay, so everybody see that? You see, you guys can't do that on a test. You know what I mean? Okay, -72. That ends up giving you for your final answer, this is what, -21?
Y'all,
Yes,
Go back to the lab.
-21. And then the same thing with this situation, the answer ends up being -20. Yes? When you do the math, you get those?
Yep.
Okay, great. All right, so the idea is look at your graph on your calculator. If I had 45 down and I look at this graph right here, what a wonderful opportunity to see something is wrong. And you're gonna have time on the test to do this. Find it, okay? Look at the graph and make sure your answer is right. So thank you for speaking up about the -21 and -20. That was a good move. All right, so any questions about that now? So the goal though, remember the goal of, on the worksheet that I asked you to be doing was to do a sketch and to find that the local min happens at, so the local min, I'm gonna go back to my iPad. And you guys go back to your sheet. I don't have the sheet right there, but I do have the situation here on my screen, what I've got done here. So the local min happened at -21. So 2, -21 should be your answer. And the local max should be 3, -20. Okay? So those are the answers. Sorry about the algebra mess, but you guys, that's okay. That's a good mistake. You guys make sure you're solid on that. You understand why the mistake I made. And do you see what happened? I left off the 6 on that 30, okay? I just wrote a 3. And that right there killed me, all right? And it killed the problem, so you gotta be careful. Any questions? Is there any step of that that's not clear?
I can't really see the change in the f of 2.
F of 2? Which one, F of 3?
The one where you forgot the 6.
Okay, you want me to go ahead and finish that one? Do we do that?
Yeah, if you don't mind.
Okay, no, that would be great. So let's do F of 3. I'm gonna go off, we know the answer to -20, I'll get a formula. Tell you what, I'm gonna go to a new screen and I'll come back to the screen if we need it, but it's, okay, let's do this. Okay, so we've got f of x equals -2x squared. Thank you for asking about this. X cubed plus 15x squared minus 36x plus 7. So we got f of 2, and the answer turned out to be -21, longhand. F of 3, let's do this. So we got -2 times 3 cubed plus 15 3 squared minus 36 times 3 plus 7. Hey, listen, you guys, if we were in a classroom, sometimes that's happened to me in class to make a mistake like that. And I use it as a teachable moment. I use it as something to say, come on, if you make a mistake, you need to do something to check and verify. Okay, that's a mistake I made. So, and the part of the situation is that it doesn't mean I don't understand the math. And that's got to do the same thing with you. That doesn't mean you don't get it, but you got to show me on an assessment that you get it. So you need checks and balances to verify. Look at a graph, make sure it makes sense, and go for it, okay? And I think that working with this, working through it, anyway, it's a good thing. Thank you guys for speaking up and smiling about it. Okay, so we end up with, that's -2 times 27 plus 15 times 9 minus 36 times 3. And that turns out to be, got to carry the 18, so that's -108. Carry the 1, and that's plus 7. So I'm going to go ahead and multiply this out. I get -54 plus 90 plus 45 is 135 minus 108 plus 7. Okay, now I'm going to do I'm going to put these two together at the front. Let's do one step at a time. That's what, 81. If I take 54 away from here, I get 81. And I get 108 plus 7. That's equal to minus 101. Okay? And that ends up giving us minus 20. So the coordinate, so that means the local max is equal to, is at the point 3, -20. Another way to say it would be local max equals -20 at x equals 3. And anyway, say that's telling me it's clear. You understand the material in that sort of a fashion. This says it too. Sometimes separating it in that fashion can clarify the circumstance. And again, the same with local min then, if I wrote it in this format, would be 2 -21. And make sure it makes sense. So local min equals -21 at